reflections. I love this picture. Because, yeah, that's a reflection. It's exactly that. A mirror image. So reflected images are the mirror images of a pre-image. So if my mountain here is the pre-image, this is the image. Images of reflections, again, I don't know how to say this word. I think it's isometry. But they're congruent shapes, but just transformed in a way where this might be called these the flips, right? FL flip. Line reflection. So we'll look at those first. The mirror line is called the line of reflection. And the image is a flip of the pre-image. We can reflect over any line we want. For our purposes, we're going to be looking at reflecting over the x-axis, the y-axis, the line y equals x. Remember what y equals x looks like? What does y equals x look like? It's got a slope of what? 1. And a y-intercept of? Oh my goodness, I know what we need to review. What's the y-intercept? Remember y equals mx plus b? Yes. So b would be the y-intercept. It's 0. The slope is 1. Remember how that works? Up one, right one, up one, right one? Or down one, left one? So this is y equals x. So if you're reflecting over that, you could go this way. What does y equal negative x look like? Well, what's the slope of that one? Negative 1 with the same. We're in big trouble. Remember that word, slope is negative 1? Put it over 1, that's a down and a right. Down one, right one, down one, right one, or up one, left one. So we're also going to be looking over reflecting this line. And you can reflect over any line. As a quick review, what does this line look like? X equals 3. Suppose I wanted to reflect over x equals 3. What does that line look like? Yeah? It's a vertical line that goes through like this point through. Right? Remember that? What about, and I can reflect over that. What if I want to reflect over y equals to negative 1? What does that one look like? That's our horizontal that goes through negative 1. So sometimes that's a confusing piece in algebra, so I just wanted to review that. So here we go. Here's a reflection over the x-axis. So here it is. That's your mirror. It's just if I fold the paper right here, and then, you ever do those ink drawings in kindergarten? You get the same image on the other side. That's how you reflect over it. So when you reflect a point over the x-axis, see how the x value is the same for both of the image and the pre-image. So x doesn't change. The only thing that changes is my y value becomes negative. So when we look at this mapping, you take an xy pair, and you keep x the same, and you take the negative value of the y value. Which means, of course, if the y value is a negative number, it becomes positive. So you're taking the opposite value, and that's how you flip across an x-axis. If you're going across a y-axis, now the y-axis is my fold line. Again, my ink picture will show up on either side, symmetric from this axis here. When you reflect a point over the y-axis, notice how the y values are the same. Oh, because that one goes to that one. The y values are the same, but what happens to the x is it is on the opposite side, so it becomes negative. So if you have an xy pair, your y value stays the same, you negate your x value. And y equals x, a little bit harder to see what really happens here, but let's look at the points here. So here's my fold line. If I fold this one over that one, or that one over this one, makes sense how these pictures look like that, if you think about it, like an ink drawing. Right? So what happened to my xy values? A was negative 4, 2, A prime became 2, negative 4. B was negative 3, 1, B prime became negative 1, 3. C is negative 5, negative 2. Transformed, it became negative 2, negative 5. So what happened? What's the mapping of these xy pairs? What is it? The switch. So if you have an xy pair, turn them around to yx, and you have the mapping for a reflection over y equals x. Y equals negative x, you're going this way now. So if you're at 0.25, what did it become? It became negative 5, negative 2. What kind of mapping do we see here? Enter. Flip of them negative. Flip of them equal negative, that's exactly right. So xy becomes, again, y equals x, just turn around, but this time you want the negative. Because we're going over the other line here. Okay. Now, vertical or horizontal lines, it's a little bit hard to come up with a rule for them. This one I do count boxes as much as I hate how many boxes. So if I have a line of reflection here, and what is this line of reflection? What's the equation of this line? X equals -2. So here's my pre-image, and I want to reflect it over there. So it's going to be proportional equally distant from that line of reflection. So if I look at B and I can see that it's one away, then this one is going to be one away in the opposite direction. Now I am noticing that this is parallel to the y-axis, right? Now remember in the y-axis, our y stayed the same, and the x's were negated. So your y's are going to stay the same too. So anytime you're going over an x equals a number type of a line, because this one's x equals 0, isn't it? Right? Isn't that the y-axis? So your y values stay the same, it's just the x's are going to be different. So you count one box over and make the point C that is -1. A, let's see, I'm 1, 2, 3 boxes away from my line of reflection, so I'll be 1, 2, 3 boxes away over here. I just find it easier to try and figure out the rule for these. If I'm looking at a y equals 2, that's parallel to y equals 0, which is the x-axis. With the flipping over the x-axis, remember we didn't change the x value. We still don't change the x value, but our y value would change. And I still think it's easier to just say, well, this one's 1 away, so that match would be 1 away as well. So if this one here, B, which is 1, 2, 3, 4, 5, 1. So what's B prime going to be? Well, it's going to be the same x value, and then I went up 1, so 1, 2, 3. And we have it. So you can use midpoint formulas. It's very complicated, I think, complicated, but harder to try and just come up with the mappings rather than just count the boxes. So that's what I do. I do this one. Some people like to actually fold the paper and look, and then they kind of put the points on it. That's a strategy as well. You can do that. Fold the paper on your line of reflection. So what do we have so far? Okay. Do we have to know these? Are these on the formula sheet? No. So you do have to know them. These, I think, are two parts to figure out. xy goes to x negative y when you're going over the x-axis, going this way. So your x's stay the same, your y's become opposite. You're going over the y-axis, your y's stay the same, but your x's are opposite. Y equals x means flip them. Y equals negative x, you're flipping and negating. For other vertical and horizontals, I would just count boxes. I think that's the easiest way. Another kind of reflection, the point reflection. Point reflection. Let's see. A point reflection exists when a figure is built around a single point, called the center of the figure. That's this one. And what happens to it? For every point in the figure, there's another point found directly opposite. So A has an opposite, A prime. Such that the point of reflection becomes the midpoint of the segment joining the point of its image. So if you were to draw a line here, it's like the distance here has to match the distance here. So here's C, the distance to your point of reflection, keep going that same distance, you get the other point. The distance here, keep going that same distance, you get your point of reflection. Now, we haven't talked about rotations, we will in just a moment, but think about what a rotation does. You're turning it, 180 degrees around. So point reflections are the same as rotating 180 degrees. So look at this guy here. Let's see if we can, is it a flip? Well, think about it. If you turn it, is it flipped? I think if you rotate it around, so if these are like, you really have to picture this in your head. You're trying to picture this turning. I mean, it kind of is a flip too. You're flipping this way and then flipping that way. Or you can think of it as turning. Yeah, well, it's a turning or a flip and a flip. So, I'm just looking at my mapping here to see if I can come up with a rule. So this one, A is 1, 4, and A prime is -1, -4. B, that one's 1, 2. When I do all the work here, B prime becomes -1, -2. Are we seeing the pattern that's forming after you do a point reflection? What happens to it? XY becomes what? Yeah, what does it become? Negated. So you take the original point, make them negatives, and you've done a point reflection. So it's easier than looking for midpoints and distances, and you could do that, but yikes. So here's a U try, a couple of U tries actually. First one, I want you to do some line reflections. Same with B, and in the okay, yeah, I should look at this these words. When it says graph the reflection of ABC in the origin, like, say what? That means that my point of reflection, and by the way, the only point of reflection we're going to be using is the origin, 0, 0. So this means point reflection. Around point 0, 0. So what's your mapping here? X, Y, negative X, negative Y. So the little, on the front of your notes, that little cheater sheet that tells you what all the mappings are, you probably want to look at that a little bit, going back and forth, because I really want more than mapping. Here's what I really want to see, and what I will ask on the test, is you take the original points, in addition to graphing them, I want to see the original points, and I want to see the mappings, how you got to A prime, B prime, and C prime. So I'll just do this guy right here. So what is A? If A is negative 2, 6, and I'm doing a point reflection, what is A prime? Just one person? What's it going to do? What's it going to do? Yeah. Right? It says take whatever x you have, make it negative, because it's already negative, make it positive. This one becomes 2, negative 1. This one becomes negative 3, negative 1. I always do this bit first. Then what you do is you're just going to graph negative 2 and 6. 1, 2, 3, 4, 5, 6. Label points always. When do we label points? Always. Negative 2, 1. So here's my original pre-image. 1, 2, 3, 1. Here's triangle ABC. I want to know what its point reflection is. That's what it means, a reflection of in the origin. So I look at my A prime. That's going to be 2, negative 6. 1, 2, 3, 4. And I'm expecting to see this thing upside down, right? I'm rotating it 180 degrees. So that's A prime. B is 1, 2, negative 9. And C prime, 1, 2, 3. Is that a point reflection? It's totally this to this, and C to C, and B to B, or you can just get away. Or think of it as you rotate it upside down. Okay, so that's a point reflection. I'll just work a little bit with these line reflections. I mean, more than anything, I really want you to practice what are the original points, and what do they map to. So, let's see, 4. 6, 3, 3, 2, we're given those. X-axis, what's the mapping? I always like to write it right on top. X, Y goes to, and X-axis right there, so the X stays the same and the Y again. And if you can't remember, you can look at the little chart until we do get it in our memory. So, what's that going to be? The X stays the same, that becomes negative. X stays the same, that becomes negative. X stays the same, that becomes negative. And then you can go up in the graph. So let me put in 2, 4. What I'm doing is I'm having a little trouble seeing what I'm doing here. 1, 2, 3, 1, 2. I hope that's right. I think that's the pre-image. And now I'm going to do the x-axis one. 1, 2, 1, 2. So that's the reflection across the x-axis. So you do the ones for the y-axis. What's that mapping? The y stays the same, and the x changes. And then for x equals negative 2, sketch it in and do some counting. And hopefully that will show up. So give these a try just to kind of get used to doing it. When you're doing a second image on the same graph, use a different notation. Here's a prime, here's a double prime, and this one becomes negative 2. and so on. This one will be E double prime. When you do this one, we're going to have triple primes. Quadruple prime. I think I'll put up the what I got here. Let's see. I don't know how readable that is. We'll get rid of some of my stuff I wrote on top. Maybe that'll make it a little bit. So it should be something like that. Good luck with that. Maybe check these that we kind of match. And maybe that'll help. I don't know. For the test, that's a good question. I want to see this, label points. I want to see your mapping. I want to see your prime coordinates. And I want to see your image. Labeled. A prime, B prime, C prime. So that's all the things I want to see. Now, I'm probably not going to ask one of this before. How would I grade that? Would you imagine? Yeah, but you can. So take a look to see how that's going. If you're on the right track, and I'll turn it in a moment. We'll look at the other one. Let's just look at the other one. So this was y equals x. So first we're going to go over this line, right? And then y equals negative x. That's the other way. So if I graph triangle ABC, it's going to be somewhere, and then we're going to turn it over. So where's ABC? ABC's over here. So when I graphed over y equals x, so that's like I folded the paper here. The image is going to be on this side. So hopefully that's where your image showed up. And if you're folding the paper this way, an interesting question, I think maybe it's, how come this came out the same? It's like the mapping didn't change from A. When I went over y equals negative x, A was 4, negative 4. When you turn it and negate it, you get the same thing because it was right on the fold line at that point. So when you're on the fold line, it's just going to be on the same spot. So I know everybody isn't there yet, but is this kind of making sense at all? Please ask a question if you're like, I have no idea what this is. Okay, we're going to be looking at the next bit. I just passed out that paper. Does everybody have it? It says rotations on it. Everybody got that? Okay, rotations. This is, if you've been to California, adventure in California, of all places. This is in Disneyland. What they did was they took the parking lot of Disneyland and made a whole other park there. So this is like a big giant Ferris wheel they have over in California. Anybody ever been there? Just me? Just me. Okay, it's fun. What do you think? Oh, good. It's fun. You're in California, go. Anyway, a rotation is a turn. Turn, right? So we're turning. It's rotating around a fixed point. We call that the center of rotation. Rays drawn from the center of rotation to a point, so I can have an angle of rotation. So here is A and here is a prime. It's transformed point. So if you draw those lines, you get an angle of rotation. So this is rotated 90. And notice I'm going this way. The normal rotation is a counterclockwise direction. Now this used to be kind of a no-brainer. Now with digital clocks, does everybody know what clockwise and counterclockwise mean? What is clockwise? If you think of a clock, an old-fashioned clock, which way do the hands go? This way, right? That's clockwise. That's what we mean by clockwise. What does counterclockwise mean? You're going against that. So counterclockwise is the normal rotational direction. These are isometries, meaning you do get a congruent shape, but look what's happened here. A has turned, B has turned, and C has turned. So you're rotating it 90 degrees around that point in a counterclockwise direction. That's the normal rotation direction. We call those positive angles of rotation when you go in a counterclockwise way. So that's the positive. Now if you go the other way, you can have such a thing as a negative angle. It just means you're next when you get to your clockwise. So if I look at my figure here, this is my pre-image. Here's a 45-degree rotation, positive. So I took this guy and I went in that counterclockwise positive direction. If I want to go in a negative direction, that's going this way. And here he is 90 degrees on his side. Where would 180 be? Upside down cat? What about 270? Like 180 this way. And then 270 is the same as negative 90. So you can get at it from different directions. So if I'm starting here, here is 45, but what would 90 look like? Cat laying on his back. 180, does it matter if you're going negative or positive? You get the same image whether you're going negative or positive. This is straight upside down. And then this is the negative direction of rotation. So if I go negative 270 from here, here's 90, 180, 270, it's the same as going positive 90. Yeah? I guess it doesn't. I think we almost always say 180, but there is no difference. It does mean the same thing, unless it matters which way you start your rotation. So just a little bit of terminology. So normal direction, this way, that's positive. This way, negative. A figure may be rotated any number of degrees. For simplicity's sake, we're only worried about these and their negatives. You might be going negative in these directions. Okay, so here's the rules. If you're going 90 degrees, you're looking, you start with your XY pair. Now you turn them kind of like what we did with y equals x, except the negative goes in front of the y now. And I was trying to think of a good way to remember that. I think if I'm going 90 degrees, let's say I start here and I go 90 degrees, I'm here. So I go negative and then I go positive, right? So I know it's going to be negative and positive. How I remember it. A 180 degree rotation, that's when you're turning this thing upside down. If I was turning this thing upside down, I'd be in this quadrant, which is a negative and a negative. So you make them negative. If I was going 270 from here, I'd wind up in this quadrant, which has a positive and a negative value. So a positive and a negative value. Now you have to turn, this one you do turn the y's and the x's, and this one you don't. That one you just got to remember that guy. But I think the hardest part is what are they negative and when are they positive, and that's just how I remember it. I don't know what's going on. So, but yes, do I have to memorize that? You sure do. You have to remember that. But if you can remember these mappings, you can do the rotations pretty easily. So let's do this example here. Where's this example? Oh yeah, on the front. So I've got a quadrilateral RSTU with vertices 3, 1. Okay, so let's graph that. All right, everybody know where we are? So 1, 2, 3, 1, that's R. Label your points. 1, 2, 3, 4, 5, 1. And label your points. T is 5, negative 3. Everybody doing that? I see a lot of people not doing it. And then U is 1, 2, negative 1. Hope I did that right. So this is my pre-image. Rotate. Then it says rotate the quadrilateral 270 degrees about the origin. The reason I'm saying that is because you know how you can rotate around any point you want? So if I was rotating around this point, I would get a different image than rotating around the origin. And for our purposes, we're always rotating around the origin. But if they had wanted us to rotate around this point, you'd have a whole different, you'd have a whole different situation. So we're going around this point. Okay, this is 70. What I do is I write the rule down. I have to. It just makes me see it. So a 270 degree rotation. Well, let's see. That's the one where you start with XY. And I know I have to turn my Y and my X. Now let's see. 270. If I started here, it would put me here. And that's a positive and a negative. So I think it's this one, a positive and a negative. Am I right? Yeah. So I can't memorize. I'm just horrible at memorizing, so that's how I remember where they go. Does that little trick make sense, or am I confusing you more with that? No. Like, if I'm over here, like let's say this is here's my little picture, my smile face. If I were to rotate him 90, wouldn't he be over here, probably? In this quadrant somewhere? So how do I get there? It's a positive, a negative and a positive. So it's going to be a negative positive mapping. I just have to remember to turn these guys. If I was to go 180, he's probably going to be in here. So that's a negative, negative. Now this one I don't turn them. I'll have to remember that. But negative, negative. And then if I was to go 270, then he's probably over here someplace. I get there by a positive and a negative. So a positive and a negative. And this one I just have to remember. I do turn it. It helps me remember it. Because if I'm memorizing junk just randomly, I can't do it.
What if it's like on the line?
Well, and that's just to remember this rule. I'm just remembering this rule.
I write down that rule, I get rid of this. I don't need this anymore. Because once I have the rule, I'm okay. Right? I write down what R, S, and U are, and now I'm going to write what they map to. So R prime, you turn Y and X, and then this part, the X, this 3 is now negative 3, because you negate it now. For the S, so I'm going to turn them, but the X, when it turns, becomes its opposite side. Kind of switch places, and your new Y value is opposite. Switch places, and your new Y value is opposite. It just so happened in this case they all became negative. If you had some, any of your X values had been negative to start with, they would go positive. Now I go to graph them. Let's see. 1, 2, 3. There's our prime. 1, 2, 3, 4, 5. That's S prime. 1, 2, 3, 4, 5 is, what's T prime? And U is negative 1, negative 2. This one. Oops, so wrong. This one. Sorry. And it should kind of look like you turned it 3/4 of the way around. Does it look like I turned it 3/4 of the way around the circle? I hope it does. Yeah, I mean, yeah. You gotta turn yourself around a little bit. So, or you can just find, where does it go? I can't do it in my head, by counting boxes. I just find it way too difficult. I remember the rules, I'm no problem. Yes or no? Ready to try it? Yes. Yes or not? Okay, so you're going to wrap this quadrilateral. So, write your points down, just get you started. Right, here's your pre-image values. And then they're going to be mapped to some new values. And which way are we rotating? 90 degrees. So write your rule. Each xy pair, what's going to happen with 90 degrees? Well, I turn them, right? And then who gets to be negative? This guy, right? Isn't that the 90-degree rule? You may look at your chart, but if you can kind of figure it out without the chart, the sooner you can do it, that's good, because you don't get the chart with that. So go ahead, fill these in, graph the pre-image and the image, and then try the other guys too. I've got the first one up here, so let's finish the first one. Anybody have a question? Please raise your hand. I think if you don't want to do it in front of the group, that's fine. But I just don't want you being frustrated and making it any harder than it needs to be. It's probably simpler than it is. Anybody having trouble? Okay. Oh, you have to grab 3 of them here. Putting up the answers. I don't know if that was going to help you, but again, keep working if you're still working on it. I'm just kind of putting them up for posterity here. But we can talk about that in a moment. So we'll go back to this one, and I'll just wait a moment to give you a chance to work on it. All right, so let's look at the last little bit we're going to be doing today, which is dilation. And again, you may have had this already. This is a proportional change. So when you get your eyes dilated at the eye doctor, right? They keep the little pupil, they make it into a big pupil. So it's that same kind of idea. It's an asymmetric thing. Dilation is a transformation that produces an image that is the same shape as the original, but a different size. When we say same shape and different size, you should think of a word, similar. So you'll get a similar figure, but not necessarily congruent. So dilations either get bigger, they're enlargements, or they're reductions, they get smaller. We tend to use different words for these in math. Sometimes you'll hear the word stretch and shrink. Sometimes you'll hear compress for this word. But a stretch makes them bigger and a shrink makes them smaller, and that makes sense. So just some examples here of things that are dilations of each other. They're not isometries. You don't get congruent when you're done, but you get similar. Center of dilation is illustrated below. So here's your center. So relative to that center, you're going to grow by a certain scale factor. We've heard scale factor before. They're applied to the pre-image to create the new image. This is my original, there's my pre-image, that would be the image. We multiply the points by the scale factor, just like you do with any similar figure, multiply. Given a pre-image and image, find the scale factor by dividing the image. So if you know 2 points, with whatever this nose is, 6, 8, and then this one is 3, 4. What's the scale factor? What is it? Well, if I'm starting from here, this is my original one, I got to here. Right? Start. Finish. Right? This is the pre-image, this is the image. What is the scale factor? 2. So you divide the image by the pre-image. So 6 over 3, 8 over 4. Okay. Scale factor is bigger than 1. Guess what? You get something bigger. If you multiply by something smaller than 1 and 0, you get a reduction. Because what are numbers between 0 and 1? A fraction, right? So they're bigger to get smaller. Makes sense. Inequality plane, here we go. We're always using the origin as the center of dilation. Doesn't have to be though, but that's what we're doing. So here's the rule. It's a very simple rule. Each xy, if your scale factor is k, you just multiply both the x by k and the y by k. Very simple. We like simple sometimes. Simple can be boring, but sometimes we're okay with that. So we're going to draw the dilation of triangle ABC with the center of dilation at the origin. If it doesn't say where the center of dilation is, we're going to always assume it's the origin. Okay, so A is -2, -2. And I'm on the back here too. Hopefully you're following along. B is 1, -1. And C is 0, 2. Whoops. There's my original, my pre-image. And what's my scale factor? Is 2. So if I have my original points, and I'm going to perform this transformation, you multiply x and y by the scale factor. So I'm multiplying everything by 2. Hopefully I did that right. And then I just have to find it. So I'm going to do A. Now so we go A prime is 1, 2, 3, 4. B prime is 1, 2, 3, 4. Prime and 0, 1, 2, 3, 4. So that is proportionally 2 times bigger, and they're all relative to the origin. And that's basically all there is to, I'm going to do this one. I think I do. Looks right. That's kind of all there is to dilation. Very simple. What else we got here? Another example. Got a pentagon. Here are the points. Why don't you go ahead and just do this one? Let's do this at the same time. Let's see if we meet in the middle here. So go ahead, graph your pre-image. I do want to see the mappings on the side. So do make the mappings as well. Checking out my scale factor here. If you want to write your rule, you can do that. So this one is going to be very clear. Right, yeah, multiplying by 1/3 is dividing by 3. Oops, no, do better if I had a better graph for this. The little, the boxes are pretty close together, but this is what I have. So again, if this one works, I hope not. So you got a couple for you to try. Once you finish this, go ahead and try some of these U-tries. Use a dilation of 3 for this one. This one you're finding the scale factor. This one you're also finding the scale factor. Your paper for letter C, they're hard to read because it didn't copy well. So look at me. Look how nice I am. I wrote out the points for you. I know. You're welcome. For this one, it's not enough boxes. There isn't. I gave myself plenty of boxes. You are going to need to just go outside and do the rest estimated. For letter A. But at least I graphed it for you. And I'm putting up the results here. You can look at them when you're done. So let's see, this mapping diagram is adapted from this thing, which comes from Grieser Prep. I'm trying to think now, Word or .com, I can't remember. But if you do a Google on Grieser Prep, is it .com or .org? I can't remember. Huh? Look for this. They've got some really good stuff on there. So this is, they use a little bit of a different notation here. Reflection over the x-axis, reflection over the y-axis. So check your work here that you got this right for the ones that you have on there, and then use this as kind of your reference point. Please make sure you always put x, y's in parentheses. I will mark things wrong if you don't give me x, y pairs in parentheses. Now, if you want that notation, make sure you have everything in parentheses. I'll just keep this up there if you are still working on that little chart.